Good evening, everybody. I do want to welcome you to the first review session of the spring 2012 semester at the online review session. And for today's session, of course, we are going to use the chapter 14, OWL, end of chapter problem set. Hopefully this session should last about about 1 hour. Jessica, go ahead and read this question for us. The first question here.
Draw the product of the Diels-Alder reaction of a following diene with this molecule. Make sure you show the full stereochemistry of the reaction product.
Okay, very good. So what they want us to do here is to draw the product of the Diels-Alder reaction of this diene, which is this molecule here, the Diels-Alder reaction between this diene and this diester right here. Of course, they also want us to show the stereochemistry. So what I've done here, I'm going to go to my writing notebook so we could do this problem together. Okay, so this is the problem we have to deal with. If you take a look at this, the way this is written, actually you see the single bond and you see the carbon-carbon double bond right here and another carbon-carbon double bond. So this is a conjugated system. Of course, the two carbon-carbon double bonds are being separated by the single bond. You also notice here that these two carbon-carbon double bonds, they are on opposite sides of the single bond. So we say this particular conformation is what we call the trans conformation. With respect to the orientation of the double bond with respect to the carbon-carbon single bond. So let me go ahead and draw the structure here and then see what we can do with this. So we have carbon-carbon double bond, hydrogen here, and here we have the CH3, and here we have the carbon-carbon double bond, hydrogen here, and here we have the methyl group. Now, so what we want to do here, before we could do the Diels-Alder reaction, since we have this molecule here written in the trans conformation, the first thing we want to do is to convert this molecule to the cis conformation. So does anybody know what we need to do to do that conversion? How do we convert this to the cis conformation? Yes, go ahead.
You have to rotate the carbon. So you can rotate either one of them. The top one, you rotate it like 180 degrees.
Excellent. So therefore, just as that was the key here, so we have to rotate this carbon-carbon single bond in order to obtain the cis conformation. So let us do that. Somebody asked a question. Sinead, go ahead. Ask your question. Okay, Sinead, do you have a question? Okay, maybe that was an error. Okay, so let us go ahead and rotate this carbon-carbon single bond. And if we do that, what we get is going to be this here.
Dr. Arende,
Yes.
I wanted to know how you know that it's trans.
Okay. It is trans. Okay, if you look at this carbon-carbon single bond, okay, this here, well, let us use this one here. If you look at this carbon-carbon single bond, okay, now, this double bond is on this side. Think of it as being on the right side of the carbon-carbon single bond, pointing to this direction here. On the other hand, the other double bond is on the other side, is on the opposite side of this carbon-carbon single bond, pointing to the left side of this single bond. Do you see that? Okay. Now, if that is the case, what we want to do, okay, I see that you see that. What we want to do is to ensure that both of the carbon-carbon double bond are on the same side of this carbon-carbon single bonds. Okay, so that is what we want to do now by the rotation. So when we do the rotation, we will then get this here. What we do, we rotate this carbon on top, okay, so that this metal now will be here, and now you have the carbon-carbon double bond, will now be here. So now what we have now, we now have the molecule in the cis conformation. This is what we call the cis conformation. Now, once you get your molecule in the cis conformation, then you could then do your Diels-Alder reaction. So let us do that now. Okay, let me take this out of here so we have some room. So we have a methyl group. And then we have this molecule, the dienophile. This is the diene. So now we're going to now have the dienophile, which is this here. They also tell us it is a cis molecule. So that means the ester functionality is both of them are on the same side of the carbon-carbon double bond. Okay, so now once we do that, this molecule, the reaction is now set up for us to see the Diels-Alder product. So essentially what you need to do, just connect this carbon here with this carbon of the dienophile and this carbon here with this other carbon of the dienophile. Keep in mind that for Diels-Alder reaction, you always obtain a 6-member ring as a result of the Diels-Alder bond formation, in which case you have two carbon bonds are formed at the same time. So what is the product here? We have a 6-member ring. Now I have a double bond here. Keep in mind that as a result of this reaction, a double bond will be formed right here, where you add the original carbon-carbon single bond, and then you have okay, of course, this metal is still here, another metal is here. In order for you to see this better, let me use this here. Let me use a red pen. to show, okay, to show the carbon of the dienophile, okay, so that you see that carbon right here, okay. Is that clear to all of you? Yes.
Would we have to show stereochemistry for those two methyl groups that were originally on the diene?
Well, you know, in this particular instance, this methyl group and this methyl group, they are attached to the carbon-carbon double bond. And keep in mind that this carbon is sp2 hybridized, and this carbon is sp2 hybridized. So in essence, it is simply just a flat. This would be a planar molecule right here. So you do not need to show a wedge or dotted line convention to represent each one of these methyl groups. You do have to show stereochemistry to get. No, in this particular instance, you do not. For the carbon-carbon double bond, all you need to do is simply just write the molecule as we have it here. You don't need to show a wedge and dotted line. Keep in mind, whenever you are dealing with sp2 carbon, the sp2 carbon is flat, and any atom that is attached to it is also on the same plane. Okay, so for here, you show the stereochemistry here, of course, which means that this hydrogen that is here will be coming at you. So very often, I might expect you to do that. Okay, so that is the stereochemistry that you have to show there. Okay. Is there any question on this before we move on? Okay. Okay, very good. Let's go to the next one. Okay, supposing I give you this. Okay, supposing we have that. Eric, go ahead and read this question for us.
Draw the product of the Diels-Alder reaction of the following diene with hydrogen, two hydrogens, carbon, carbon, hydrogen, carbon, oxygen, carbon, and three hydrogens.
Okay, very good. Okay, let me ask you, all of you, at this point, what is the conformation of this this conjugated diene that you have here? What is the conformation? Trans. Excellent. Trans. Excellent. So now what do we need to do in order to prepare this molecule for Diels-Alder reaction? We rotate, exactly. We have to rotate this carbon-carbon double single bond. So let us do that. Let's draw the original molecule. The original molecule is this. You have a double bond here, and then we have that is attached to double bond here. So what I am going to do, what I will do here is to simply rotate on this carbon-carbon single bond, and then so once I do that, I will obtain, I will go from the trans conformation to the cis conformation. So now I will obtain this. Now we have this. Now the double bond is here. So now we have the cis conformation. So at this point, what I need to do now, we have our diene. And then I will now have to introduce the dienophile, which is this molecule here. And that is CH2. Okay, attach the carbon-carbon double bond. And then you have this here. Okay, so now we could now from our Diels-Alder product. Okay, so you could simply just imagine that you are joining this carbon to this carbon, and you are also joining this carbon to this carbon. So therefore, you form your 6-member ring. This is carbon number 1, 2, 3, 4, 5, and 6. So let us go ahead and draw that. I see Jasmine Godin has joined us. You are welcome. Okay, so now we have this. Now I am going to use the red. Let me use the red to, of course, the double bond is now going to be here. Okay, so we are going to join this to this. Let me use a red pen to show the bond from the dienophile. Okay, and of course now we have here and of course we have here hydrogen here, and another hydrogen here, and here will be hydrogen here. Okay, do you guys see that? If you see that, give me a happy face. Okay, so you can see here in most of these cases of Diels-Alder reaction, the process is fairly very simple. Simply joining the 1,4 carbon from the dienophile. In this case, if you say this is carbon number 1, carbon number 2, I'm sorry, the 1,4 carbon of the diene, say carbon number 1, carbon number 2, carbon number 3, carbon number 4. So we join the 1 carbon to one of the carbon of the dienophile, and the carbon number 4 of the diene to the other carbon of the dienophile, and that is how you form your 6-member ring. Okay, so now let us go to, let's see if we can do this. Okay, here, let me see here. Emma, go ahead and read this question for us.
The image below is that of an allylic carbocation intermediate formed by the protonation of a conjugated diene with HBr. Draw the structural formulas for the final reaction product.
Okay, very good. It also says if there are 2 products, draw both in the same sketch. Okay, so in other words, if you expect 2 products, go ahead and draw the 2 products. Now, keep in mind what they have here. They say this is the allylic carbocation. If this is the allylic carbocation that is formed as a result of the electrophilic addition reaction of hydrogen bromide with a diene. So what this is telling us is that the proton has already been added. So let us take a look at this molecule here. So let me draw this here so we could see this better. So we're starting with this methyl group. So we have a methyl group. Then we have this carbon attached to hydrogen. Then we have that carbon attached to another carbon which is attached to hydrogen, and that is this one here. And then we have this carbon here attached to a methyl group. which is this carbon attached to this methyl group, and then we have this carbon. We'll be able to access this later. Yes, Brittany. Yeah, that is correct. The webcast will be posted in Blackboard tomorrow morning. Okay. Okay, so therefore you have a CH2 right here, and then you have a CH3. Okay, so now they tell us this is a carbocation that is formed as a result of the addition of this proton to a conjugated system. So now the question is, taking a look at the skeleton of this molecule that we've drawn here, where is the carbon-carbon double bond, and where is the carbocation? Okay, let me just number this here so that we could use this for reference. Supposing I say this is carbon number 1, just for reference, 1, carbon number 2, carbon number 3, carbon number 4. Okay, supposing I do that, and then I say this is carbon number 5. Okay, just for reference again, I'm going to say this is carbon number 6, carbon number 7. Okay, now let me ask you this. Where do you think the carbocation is, and where do you think the carbon-carbon double bond is? Okay, carbocation is on is on C4. Excellent. Very good. Does anybody know why the carbocation will be on C4? The double bond is between C2 and C3. Excellent. Great. Okay. Most stable. Great. You guys are you guys are rolling. Okay. So that is correct. So therefore, just as you guys are suggesting here, the double bond is here, and the carbocation is here, because that is a tertiary carbocation. So which means, therefore, if you look at this molecule originally, the chances are that the carbon-carbon double bond was here, or it could also be here. Okay? So therefore, the hydrogen could have added to this carbon to form the CH2, or it could have added to this carbon to form a CH3. But the point here is that whatever it does, it will form the more stable carbocation, which is the tertiary carbocation. So very good. So now if that is the case, then we also know that we have, as a result of the addition, we do have the bromide anion is formed, because once you add your hydrogen from here, the bromide anion is formed. So now what will be the product? What is going to happen next to get the final product? What will happen now to get the final product? Anybody has some idea? Okay, the bromide will attaches to carbon 4. Excellent. So now the bromide, acting as a nucleophile, will attack this electrophilic carbon, which is a carbocation. And so therefore you obtain this product. Okay, the ethyl group is here, and this is here, the methyl is here, and the bromine is here. Now, let me ask you this. Okay, the product that we have given here, is this a result of 1,4 addition or 1,2 addition? Okay, is this a 1,4 addition product or 1,2 addition product? 1,2 addition product. Excellent. Very good. Okay, that is correct. Now, what other product can we therefore expect to get from here? What other product do you expect to obtain from here? What other product do we expect a product from the 1,4 addition? Yes, of course, yes. So therefore, to get the product from the 1,4 addition, what is going to happen? To get the product from the 1,4 addition, what will happen? Okay, what will happen to this carbocation? Resonance. Okay, we draw the resonance. Excellent. Excellent. So now we're going to draw the resonance. So we draw a resonance structure of this molecule in which we now move this pi electron to here. So now we are going to form a carbon-carbon double bond here. And which means now that the carbocation will be on this carbon. Okay, so let us draw that. So we have CH3, hydrogen here, carbocation there, and then we have this is now moved. Hydrogen is still here. Now we have a double bond here. Now this is here. And now the ethyl is here. Okay, if that is the case, what is the next thing that will happen at this point? What will be the next thing that will happen? Okay, bromine attacks carbon. Okay, this carbon, this carbon here. Excellent, great. So the bromide anion acting as a nucleophile will attack this. Now keep in mind, folks, that every time you are drawing an arrow, you draw an arrow from the nucleophile to the electrophile. You never draw arrow from electrophile to nucleophile. Never do that in organic chemistry. Okay, so therefore the product that we are going to obtain now will be this product here. CH3, bromine is now here, hydrogen is here, and we have this here, hydrogen here, carbon-carbon double bond here, and this here, and then the ethyl is here. Okay, and so that is the second product. This right here. Now, if you follow this, give me a happy face. If you don't, give me a frowning face so we could explain further, okay? I see a lot of happy faces. Very good. Very good. Okay. So, therefore, what we have here, keep in mind, whenever you have a conjugated system and you are doing electrophilic addition, you will always obtain two products. One will be a 1,4 addition product, and the other will be a 1,2 addition product. And that happens anytime you are going to be forming a carbocation. Okay, so let us go to, okay, let's see here, 4. Okay, let's do a little light chemistry here. This is nomenclature. Okay, let's see. Melat, go ahead and read this question for us. Okay, I don't think Melat is ready. Bria, is your mic working? If your mic is working, go ahead and read this question for us. Oh, okay, Bria, you have no mic. Okay, very good. Okay, Julianne, go ahead and read this question for us.
Give IUPAC names for the following compounds.
Okay. This should be very simple question here. This is what we did last semester. Okay, to give the IUPAC name for this, okay, what will be the parent name for this? What will be the base name for this molecule? Okay. No. This. Keep in mind now. Okay, this is cyclopen. How many double bonds you have here? Okay, cyclopentadiene. Excellent. That is correct. This is cyclopentadiene. And when you have this molecule here, to number the carbon skeleton here, you start numbering from the carbon-carbon double bond. Okay, that's position number 1, position number 2, 3, 4, and 5. Okay, you number this molecule here so that you give the carbon of the carbon-carbon double bond the lowest combination of numbers. Okay, so in this particular instance, therefore, what will be the complete name for this? Given the fact that we have a methyl group in 2 positions and another methyl group in 3 positions. Okay, that would be 2,3-dimethyl 1,3-cyclopentadiene. Excellent. Okay, so that would be 2,3-dimethyl. Now we indicate the position of the double bond. That's 1,3-cyclo, because it is a cyclic molecule. Penta, because it contains 5 carbon atoms. Then you have diene to show that you have 2 double bonds. Okay, very good. Okay, now let us try this. Let's try this one here. Okay, we did very well with this, so let us try this one here. Okay, what will be the base name? How many carbon in the cyclic ring system here? How many carbon in the cyclic ring system? Okay, good. Okay, so how do we start the number? Where do we start the number? We start the number from here. 1, 2, 3, 4, 5, 6, and 7. Okay, keep in mind you number so that you give the carbon of the carbon-carbon double bonds the lowest combination of numbers. Okay, so what will be the name for this? What will be the base name? Since we have 7 carbon. We have 7 carbon, okay? That is, okay, you guys you are giving me the full name. So the full name is 7,7-dimethyl 1,3,5. Excellent. So 7,7-dimethyl. Okay, now we indicate the position of the double bonds. 1, 3, 5, cyclohepta. Now, because we have 3 triple bonds, we now say triene. Okay, so you guys still remember what we did last semester. Very good. Okay, so let us move on. Okay, let us go to, okay, let's see here. Okay. Let's see. Tikia, go ahead and read this question
Predict
for us.
the product of the Diels-Alder reaction of this compound with cyclopentadiene. Draw your product in the box below.
Okay, very good. Now, this is a case in which a molecule, this is the diene. Now, this molecule also now is going to provide the dienophile. Okay, very often the carbon-carbon double bond of the diene could also act as a carbon-carbon double bond of a dienophile. So what they want us to do here is to predict the product of this reaction. In other words, the cyclopentadiene will be reacting with itself. Okay, this acting as a diene, it will also act as a dienophile. Okay, so what would that be? Okay, what I would like to do here, let me just orientate this molecule here in such a way that I will be able to see my Diels-Alder reaction much more clearly. Okay, I'll have this double bond here and this double bond here. Okay, then I have this here acting as a dienophile right here. Okay, so what we have here, we now do what we normally do. We join, we say this is carbon. If we say this is 1, 2, 3, 4, so we join carbon number 1 to one of the carbon of the dienophile, and then carbon number 4, okay, this is carbon number 4, to one of the other carbon of the dienophile. I see Melody is having a problem with her internet. She's going in and out. Okay, so the product therefore will be this here. Just draw it this way. Let's draw our 6-member ring. Okay, the 6-member ring from the Diels-Alder reaction, which means that the double bond is here. Okay, this double bond has moved here now, and then this carbon here. Okay, this carbon here. Let me use a red pen to show that. Okay, so that is this one here. And now the rest of that molecule is there. That means this double bond is still here. Now at this point we need to show the bridge. Let me use my blue pen. This bridge right here, we need to show this bridge, so which is this one here. Okay, now if I want to be very fancy in drawing this, of course it will look more like this. Looking at the molecule from the side. And the hydrogen will be coming at you. Keep in mind, we told you that you're going to form the endo product. And then this here. Okay, the endo product, so that will be, since that will be the opposite this here. Okay, will be right here. Double bond is here. Okay, that's if you want to be fancy. So this endo product will be formed. Of course, the double bond will also be right here. Okay? Okay, do you guys see that? But for the most part, if you just want to stop right here, that is fine with me. Okay, if you see that product, how we form the product, give me a happy face. If you don't, give me a frowning face. Okay, I see a lot of happy faces. Okay, very good. so we could move on. Okay, now I want to, okay, this product, okay, let's see here. Naila, go ahead and read this question for us. Okay, Naila there. Okay, is Naila there?
Two Diels-Alder atoms, and the both two observe the two structure of both products.
Okay. Okay, very good. So what they want us to do here, they say the actually they say the above reaction. It should be the below reaction. This reaction below this this is the diene and this is the dienophile. They are saying that two products will be formed, and we need to show the two products. Okay. Now, if you look at this molecule here, what kind of conformation is this molecule with regard to the orientation of the double bond? Trans. Okay, very good. So now, what is the first thing we need to do? What is the first thing we need to rotate? Okay, very, very good. So we are going to rotate this molecule so that we obtain the cis conformation. Okay, so let me go ahead and do that. I will simply say, okay, I want to rotate this. I will keep that in place. That is there. And then I have this here. And then I have the double bond will be here. And of course, this bromine is still here. Okay, at this point, I will then have, this is the diene, then I will have my dienophile right here. Okay, now, so if that is what we have, then of course think of the fact that we are going to join this carbon to this carbon, and this carbon to this carbon, and so that is your 6-member ring, and in so doing, the double bond goes here. So let us do that. Our double bond is here now. Okay, which means that we have this bromine is here. Okay, and then this here, this is the carbon. Like I would like to show this, just so we can see that better. Okay, this is the bond from the dienophile. Okay, and of course that bond you have, the methyl group is attached to here. Now that is one product, because they are telling us that we are going to get two products. That will be one product. Now what will be the other product? Anybody has an idea what the other product will be? Does anybody have an idea? Think about the orientation of this dienophile. What do you think we will need to do to get a second product here? Think about the orientation. Okay, the methyl on the other side. Excellent. So therefore, the other product will be, if we have, okay, so this is one product right here. And the other product will be, if we simply take this out, I'm sorry. We have this here. We have this here. Okay, of course, this is still here. And now we take this one out. Just like somebody said, the methyl on the other side. If that is what we do, then we are going to get this product. Get this out. So we're going to get this product. Let me do a long arrow here, in which we now have your 6-member ring. Okay, you still have your double bond is here, your bromine is here, and now this time you have your methyl group is on this side. And of course, this is the bond from your dienophile. Okay, so these are the two products that we are going to form. Okay, this here and this, because the reason why you get two products here, because you are starting with a diene that is non-symmetrical. This is a non-symmetrical diene, so that allows us to get two different products, non-symmetrical. Okay, if you see that, give me a happy face. The methyl group is missing. Somebody said the methyl group is missing on the first product. Oh, okay, thank you. Actually, the methyl group is missing on both of them. Thank you for pointing that out to me. So the methyl group will be here, and also will also be here. Okay. Here the methyl groups are next to each other, 1, 2 to each other. Here the methyl group are 1, 3 to each other. Okay, Christina, thank you very much for pointing that out to me. Okay, is there any question on this? Somebody has a question? Okay, no question. Okay, so let us move on. We're moving right along. Okay, let's do this one here. Okay, let me see. Jessica, I have not heard from you in a while. Go ahead and read this question for us.
Rank these dienophiles in decreasing order of reactivity in a Diels-Alder reaction.
Okay. Okay. What they want us to do is to rank these dienophiles in increasing order of reactivity with regard to Diels-Alder reaction. Okay. Now, can you guys take a guess as to what the ranking will be? Keeping in mind that for the dienophile in Diels-Alder reaction, the more electron withdrawing group attached to the carbon of the carbon-carbon double bond, the better, the more reactive the dienophile. Okay, somebody says D, C, D, B, A. Okay, very good. Okay, I will take this one first, because you have the carbon-carbon double bond is attached to the cyano group. The cyano group is very electron withdrawing because this carbon is an sp carbon atom. Sp carbon atom are electron withdrawing, and therefore, so because you have two cyano group here, I would say this is the most reactive. Okay, so about somebody said D. Yes, D will be the next one. I would pick D next, so it would be C, D. Why D? Because of the carbonyl group that you have here. If you have a carbonyl group, okay, the carbonyl group is also electron withdrawing because this carbon here is an sp2 carbon. sp2 carbon do withdraw electron, plus the fact that you have oxygen attached to this carbon here, which is also electron withdrawing. Okay, so it will be CD. Okay, then I will have to pick A. Very good. Somebody got it right. Eric got it right. So I will pick A because A only has one methyl group. The alkyl group are deactivating because they do pump electron into the system. So they do reduce the activity of the dienophile. So in this case, since we only have one methyl group as opposed to two here, I will say that A will be more reactive than B. So finally we have B. Okay, and so that is the order. Very good. Okay, is there any question on that before we move on? Okay, very good. So, okay, so let us go to 15. Okay, Eric, go ahead and read this question.
Show the starting diene and dienophile you could use to prepare the following molecule.
Okay, very good. Okay, do you guys have any idea what we need to do here? The diene and the dienophile. Of course, if we have the 6-member ring coming from the Diels-Alder reaction. So if we simply click right here, so this part of the molecule will be your diene. Okay, if that part of the molecule is your diene, therefore, what would that be? What would it look like? Keep in mind that this double bond here was your original single bond, so therefore that has to be this here, single bond, double bond. Now, what would be the relationship of the metal? Yes, there is a triple bond. Yes, very good. What would be the relationship? Where would the metal be here? Okay. Keep in mind they are cis to each other. Cis, exactly. Cis. So they will be going away here and going away here. So they are cis. And then the dienophile, since you have in the dienophile part, you see have a carbon-carbon double bond. So that means the original dienophile was a triple bond. Okay? So therefore it is this here, with an S-star functionality attached to the carbon-carbon triple bond. Okay. So this is a very simple one. Generally, it's much very simple to go from the product to the starting material of the Diels-Alder reaction. Okay, is there any question on this before we move on? Okay, we will do 10 more minutes before we leave. We are almost at the end. It's almost 8 o'clock. Okay, if that is clear to you, give me a happy face. Okay. Okay. Melat, if your mic is working now, can you read the next question for us? Let me see where that is. This question here.
Specify whether the compounds below have a UV absorption in the 200 to 400 nm range.
Okay, very good. So what they want us to do here is to specify whether these molecules here, any one of these molecules here, will have a pi to pi star absorption, UV absorption in the 200 to 400 nanometer range. Now this here, generally when you have the ultraviolet spectroscopy, okay, what is responsible for the absorption spectrum in ultraviolet spectroscopy is the transition of the pi electron from what we say the ground state pi electron to an excited state. That is what this is showing you. And generally the absorption is found between 200 to 400 nanometer. Now, the only time this happens is when you have a conjugated system. So in essence, what they are asking you is which one of these molecules is conjugated. That's what they are asking you. Another way of asking you that question, which one of these molecules is conjugated? Okay, so let us start with this. Let's say this is 1, 2, 3. Okay, is 1 conjugated? Is 1? No. So therefore, there will be no absorption. Okay, very good. No. is 2 conjugated. Yes. So we expect this to absorb in the UV spectrum. So yes. About 3 is 3 conjugated. No. So no absorption. So only one of these here will absorb, will give a UV absorption. Okay, that is all they are asking you with this question. Okay, that was a very simple one. Now, let us do this before we leave. We finish this and then we leave for today. This is the question of the day. Okay, let me see here who I not talked to yet. Let me see who is here that I've not. Christina, is your mic working? If your mic is working, can you read this question for us?
Beta-octanine is a pleasant-smelling hydrocarbon found in the leaves of certain herbs. It has a molecular formula C10H16 and a UV absorption maximum at 232 nanometers. On hydrogenation with a palladium catalyst, 2,6-dimethyl-octane is obtained. Ozonolysis of beta-octanine followed by treatment with zinc and acetic acid produces the following 4 fragments: acetone, formaldehyde, carbonaldehyde, malosialdehyde. Proposed structure of beta-octanine.
Okay, very good, very good. Okay, now what they want us to do now is to determine the structure of this molecule. Okay, the formula of that molecule is C10H16. Okay, the first thing I want us to determine here, what is the index of hydrogen deficiency for this molecule? In other words, how many double bonds or rings does this molecule have? What is the index of hydrogen deficiency? Anybody? Okay, 3. Bia said 3. That is correct. For those of you who do not know the formula that we use, it should be clear to all of you by now. Index of hydrogen deficiency, IHD, equals to the number of carbon atoms in the molecule minus the number of hydrogen atoms in the molecule divided by 2 minus the number of halogen atoms divided by 2 plus the number of nitrogen atoms divided by 2 plus 1. Now, if you use this formula here, you will find that the IHD, index of hydrogen deficiency of this molecule, is 3, just as Bria has just told us. And also Funke told us, Jessica told us, Christina. Very good. Okay, so the IHD is 3. So what does that mean? What does that mean? Okay, I give you an IHD of 3. So what exactly does that mean? Okay, can you just tell me what I am supposed to make of that information? IHD of 3. Okay, it means that you have either 3 double bonds or 2 double bonds and a ring, or 3 rings. Excellent. So, okay. Now, let us now look at the other set of information. Now, they also told us that this molecule has a UV absorption at 232. So, what does that tell us? What does that tell us? It is conjugated. So, that means this molecule must at least contain 2 double bonds. Okay? So, very good. Now, they now say, let us, for the sake of our discussion here, let us call this molecule molecule A. Okay? They now say this compound molecule A, when they now perform hydrogenation using some kind of catalyst, let us say we use our platinum, they obtain 2,6-dimethyl-octane, which means that they obtain this molecule here. Let us see, octane is the base name. 2, 3, 4, 5, 6, 7, 8. Okay, so the base name is octane. They say 2, 6. Okay, if you say this is carbon number 2, You have a methyl here, carbon number 2, 3, 4, 5, 6. You say there is another methyl here. Okay, dimethyl octane. So the rest of it is I will fill the rest with hydrogen. Okay, so as a result of this hydrogenation, so what they are telling us now, they have given us the skeleton, this carbon skeleton of this molecule. Now, since they have given us the carbon skeleton of this molecule, what they are also telling us is that this molecule contains 3 double bonds. Keep in mind the IHD is 3. Okay, it has no ring, so therefore it must have 3 double bonds. Okay, so now we have that information. Now the last set of information they also giving us is that this molecule that we are calling molecule A now will react with ozone followed by zinc to give all of this product here. So now we have to determine the structure of compound A. Okay, so how do we go about doing that? Okay, I look at what we have here. We have formaldehyde, this here. We also have acetone. Okay, link, link, okay, exactly. We're going to have to link the carbon oxygen double bonds together. Keep in mind, all of these carbon-oxygen double bonds were a result of the ozonolysis cleaving something here. Okay, link to make double bond. Exactly. So that is correct. Now, this is what I will do. I will start with one of these molecules, one at a time. I will ask myself here, if you take a look at the acetone, okay, so you have a CH3, and a carbonyl. How can I get that? So I'm going to say that must be this part of the molecule. Okay, that must be this part of the molecule. So therefore, what I do, I remove this here, place this here. So that means there must be a double bond here. So that means I remove. Okay, so this here will explain to me that if we clip this here with ozone, you are going to get the acetone. Now, if you see that, give me a happy face. Do you see that? In other words, if we place a double bond here, that will give us this acetone. Okay, very good. Now, so far so good. Now, then the next thing I will do, keep in mind when you have this kind of problem, you look at the most obvious information to work with. Okay, so therefore, at this point, I would therefore now say, okay, I have at this point determined where this one came from, right? So let's take this out of here in order to make up some room. Then I will now take a look at the formaldehyde, this here. For us to form this, I would say that must have to be at the end of this molecule because it couldn't be here. We already assigned the double bond to here. So it must be at the end of this molecule. So what do? I take this off, take one off here, and then I will say there must be a double bond here. Okay, if that is the case, if I clip this, that will give me the formaldehyde. If you see that, give me a happy face. If you see that, if I clip this here, okay, that will give me this molecule here, formaldehyde. Okay, so far, so good. I now need to explain one more double bond, right? Because this molecule only has 3 double bonds. Now I have accounted for 2 double bonds as a result of explaining the formaldehyde and the acetone. So now all I need to now do is to explain this molecule and this molecule. In so doing, I have to place the double bond somewhere here. Now keep in mind, this molecule also absorbs, is conjugated, okay? So whatever it is, the double bond that I'm going to have to place will have to be conjugated with the double bond or conjugated with the double bond. So it is either going to be here or going to be here. Okay, do you see that? Do you see the logic here? Because there are going to be conjugation here. Either the double bond is here, in this case, it is conjugated with this, or the double bond will be here. In this case, it will be conjugated with this. Okay, so let us see what do we have. If we now look at this here, let us look at this molecule here. Okay, let us look at this molecule here. This molecule here, you have this carbon-oxygen double bond, right? And this carbon-oxygen double bond. Between them, you have a CH2, a methylene group. So if that is going to be the case, keep in mind that we are going to cleave this here, okay? So that will give us a carbon-oxygen double bond here. Therefore, what we are therefore saying, the CH2 must be attached to this. So I would say, for me to get this molecule here, the double bond must be here. Okay? Now follow me now. For us to get that molecule, the double bond must be there, which means that if I cleave this, and I cleave this, okay, this CH2 here will be this CH2, and then this, oh, I'm sorry, I have too many bonds here. Let me take this, one of these out. Okay, since I put the double bond there. So if I cleave this, this becomes the carbon of the aldehyde on this side, and also cleave this, this becomes the carbon of the aldehyde on this side. So now, I have explained this molecule. Do you see that? If you see that, give me a happy face. Okay? So, if we say this is the double bond, now let me see, can we explain this? Can we explain this? Okay? Yes, we could explain that, because what we have here, if we cleave this, imagine that I'm going to, if I cleave this right here, if I cleave this here, okay, if I cleave that, oh, by the way, I need to take off this hydrogen here also. Okay, too many hydrogens here, because I put the double bond here, so I need to remove that. Right. Okay, so if I cleave this, this carbon becomes a carbonyl, which is this carbonyl right here, and this methyl group is this methyl group, right? Therefore, the only other carbonyl that I need to explain will be this carbonyl right here, and that is a result of cleaving this. Okay? Keep in mind, when I cleave this, I get the formaldehyde, and also when I cleave this, this will give me this. It will also give me this. Oh, I'm sorry. It will also give me this, the formaldehyde. Okay? Okay, when I cleave this part here, this part gives me the acetone. Okay? Gives me the acetone, and also gives me, I'm sorry, this one here, yeah, I got that mixed up. This here is supposed to be, this here gives me this, and this here, this part of the molecule right here, this here gives me this. Okay, so therefore compound A has to be, compound A is this molecule here. Let us draw it out so that it will look much cleaner. Compound A, therefore, will have to be this. This, okay, and then this CH2, and then attached to CH, this here, CH3, and then of course another CH3. Okay, so this is our unknown compound. It's right here. Okay, this one right here. Okay, if you see that, give me a happy face. I see somebody asked a question earlier. Do you see that? Okay, okay. Somebody asked a question. Very good. Somebody said, okay, where? Oh, I don't see. Okay, somebody said, what happens? Okay, what happens if you have to find out the structure of A from an aldehyde? Well, that's what we. Well, you know, you have to find out. The answer to that question is you have to find out the structure of A based on the information that are given to you. In this particular instance, all we are simply doing is using all of the information that we have been given. One is that the formula of the molecule that tells us index of hydrogen deficiency is 3. In this case, it turned out to be 3 double bonds. Also, the fact that when you do hydrogenation, it gives us the skeleton, the 2,6-dimethyl octane. So that gives us the carbon skeleton. And then finally, it tells us that after the ozonolysis, we get all of these products. So what to do is to use the data that you are given to construct your original molecule. Oh, you meant if you give, but that isn't the data that we are giving. You have to go by the data that you are giving. Okay, so that is essentially how you approach this kind of roadmap problem. Actually, we call this kind of problem roadmap problem, and you should expect to get this kind of problem in your exam, roadmap problem. Okay, is there any question before we leave for today? Is there any question before we leave for today? Let me see. By the way, let me acknowledge everybody that is here. I see Emma is here, Bria, Brittany, Mike, Courtney, McLinden, dear Joseph, Dylan, Eric, Jasmine Gordon, Jessica, Julianne, Christy Jacobs, Lauren Prince. I hope I'm not leaving out anybody. Melat, Nela, Seals, Lufunke, Adeleye, Robert Moore, Shine, and Simon Cohen, and Tikia. Okay, I hope you guys enjoyed today's session. This is our first session of the semester. We hope to do this kind of session every Wednesday. And if you have no question, I will say enjoy the rest of your evening, and I will see you in class tomorrow.